What we'll talk about is neural network today. As I said, not fancy. What's that? Well, what we learn is neural network is just a function. Okay, so it's just a function. So if we have function for modeling, what we can do is if it's a regression function, sorry, not regret. If it's regression problem, that means the outcome is a continuous. What we no. It's too detailed. Okay. If we have function for modeling, what's the general strategy? General strategy is what's the objective for the task? If the task is regression, the objective is let me remind you is y height square then n. Then we have a training example, right? I equal 1, we have n training example. This is square error, right? How we derive this? This is we derive this using MLE, maximum likelihood estimation, right? So generally, I call this MLE objective. You already learned that in week 5, right? Also in week 6, we also learn the objective function for classification. That is also derived from maximum likelihoods, right? We assume the Bernoulli distribution of the outcome y. So what we get is we have y log y height minus 1 minus y log 1 minus y height. So we have training data from I to n. So I calculate this for each training data. I want to minimize this. I also want to minimize this, right? That's our objective, right? We want to minimize. All good. So we already learned it in week 5. We already learned it in week 6. And we have this objective function, and we have a function for modeling the problem. This function will give us prediction y height, right? Y height. So this y height is our prediction. Which prediction is good? Look at this function, this objective function. If the objective function is give you very small values, that means the prediction is good, right? So now according to this objective function, we go back to the modeling function. We just optimize the modeling function. We optimize the beta 0 and beta 1 for the regression and for the linear regression and the classification for logistic regression, right? For linear regression, we have a beta 0 plus beta 1x. For logistic regression, we have sigmoid beta 0 plus beta 1x, right? This is a logistic regression. This is linear regression. Linear regression is for align with this objective. Logistic regression is aligned with this objective. That means in week 5, this y height is achieved by beta 0 plus beta 1x. In week 6, this y height is achieved by the sigmoid beta 0 plus beta 1 x, right? So then in week 5, I just using the I just make the derivative of beta 0 and beta 1 equal to 0, right? Then I derived what's the best value for beta 0 and beta 1, right? Because this objective function is, the convex function. When this function has a minimum value, because when is at the bottom, the derivative equal to 0, right? So that's why I make the derivative equal to 0 to get beta 0 and beta 1. I want to do the same thing for sigmoid, but I failed. So finally, what I do is I using gradient descent. In gradient descent, I still calculate the objective function. Let me call objective function L. So I calculate the derivative of objective function with respect to the 0 and with respect to the 1. I can make it to 0 and 0, then I calculate this for linear regression, but I can't do that for logistic regression. So what I do gradient descent, right? What's gradient descent? Gradient descent just means, okay, you have this gradient, you have this gradient. Now, using this gradient to change the beta 0 and beta 1 to make it better. What do I mean by make it better? That means your objective function will achieve a smaller value, right? Because you want to minimize it. So how I can update it? How I can update beta 0 and beta 1? What I do is beta 0 equal to beta 0 minus this. I also add something called learning rate. I told you what's the learning rate is because I have a, let's say beta 0 is at this point. I want to move it to this point. This point will give us the minimum value of objective function. So I minus this derivative, right? That means I will go to the opposite side of this slope. So I will go to here. The slope is negative. So minus negative is equal to positive. So I will go this direction, positive direction. So, but I don't want to go too far away, right? If I go too far away, I will move to here. You know, here is larger than here. So it's not get better, it's get worse, right? So that's why I want to have learning rate here to control. Don't move too far away. Just move a little bit step, a small step. So then you can ensure you will get a better result. So that is a gradient descent. So let me finish this. We also need to update beta 1 alpha. Okay, that's the thing. You know, we learn all of them in weeks 5 and week 6. And the only thing we want to change today for neural network, actually, we also call all this framework maybe deep learning. You know, if you go to these two terminology, neural network and deep learning, it just means you have objective function, you use gradient descent to an objective function to update beta 0 and beta 1. But now you don't only have one beta, but now what's the beta 0 and beta 1? So in neural network, the beta 0 and beta 1 will be more than one set of beta 0 and beta 1. It will be a lot of beta 0 and beta 1. That's why you said, oh, neural network is neurons. What's neuron? This is one neuron. But neuron is not only one, right? You know, in human brains, we have a lot of neurons, billion, million neurons. That's what happened for neural network. Neural network said, okay, if this linear function is a neuron, I don't want one neuron. I want million of neurons. So just give me million sets of beta 0 and beta 1. That's it. That's the neural network. Yeah, so that just means we need to change the function, right? We don't need to change the MLE, okay? We don't need to change the objective function. We also don't need to change the gradient descent. We don't need to change how we update the beta 0 and beta 1. And now we have more beta 0, beta 1, but it's same thing. We're still using this gradient descent, using the same gradient. So the only thing changes, okay, now I don't have this simple linear regression and logistic regression. I will have a more complex function. So people always call this complex function neural network. So let's go to it. Now let's say I have a feature x1, x2, x3. So for linear regression, what we do is we do x1, w1 times x1 plus w2 times x2 plus w3 times x3. Then you're done, right? That's a linear regression. That's a function for linear regression. What's the logistic regression? You get this, and you also get the sigmoid. Okay. So as I say, this can be one neuron of a neural network. Then you have the one head output, right? But what's the neural network? Neural network is like, let me rewrite it because it's occupied too much space. I need more space to write more function. As I say, neural network has a lot of function. In ChatGPT, it has a billion of this function. Of course, it's more complex in ChatGPT. This is called feed-forward. Actually, all the modern neural network are derived from this feed-forward neural network. So if you understand this, then you can understand more complex neural network. But the basic thing is just this: 2 W3 X3. Then you have sigmoid. So this is one neuron. Okay. So now we don't only have one neuron. One neuron only give you one output, right? Now I don't only want this one output. I want to have multiple outputs. Not only output one, A1, I call it A1 because normally people will call this activation, call this value activation. So I call it A1. So it will also do another linear function with sigmoid, with activation function. You don't need to use sigmoid. You can use using 10H. It's another nonlinear function, but it doesn't matter. Actually, you know what's a nonlinear function, right? Nonlinear function is just like, okay, it has some curve. So it's not like a line. So it's nonlinear function. This is the curve of sigmoid. So I have another neurons. Now in these neurons, you have to know the weight is also different, right? It's not the same. I call it weight because normally people will call it weight and bias, right? We have a B here. People will call B bias, right? So I want to put it as one because it should be different. I shouldn't make the same one. I should make it one, maybe 2, 1, not 1, 1. Here is 1, 1. Here is 1, 2. Here is 1, 3. That means the weight in the first neuron for the first feature, the weight in the first neuron for the second feature, the weight in the first neuron for the third feature. So now I also have W2, 2, X2 plus W2, 3, X3 plus B. Have sigmoid function for this. This is another neuron. So yeah, that's 2 neurons, right? So how we use 2 neurons? I think it's already there, but I want to make it view the make some line, because online, if you look at neural network, you always have some line like this. Okay, here, what this line means is line just means x1, x2, x3 attend this linear function. So also I will make line for this. So that's it. Then we have a new feature, right? Now we can put new feature as go to another neuron. Now maybe this is a last one we have, a last layer we have. You know, this is called one layer. When we go to the next layer, that means we will use this the output of the previous layer as the input of the next layer. You can take these two as a feature. So now you have another neuron. Now I have sigma I function, activation function. Now I have weight. Now it's in the second layer. This is for the first layer, so I put first layer, first layer, first layer, first layer, first layer, first layer. Now it's the second layer, second layer. Then this is the first neuron, first feature, x1. Then plus the second layer, first neuron, second feature, and W, second layer, first neuron for third feature, x3, hacken plus B. That's it. So I put this. Now I have output. This output is y height. I just say, okay, this is y height. Then I can go into using this y height to get the objective, right? That's the whole picture. But doing the implementation, you will set it's using the matrix for to do the efficient computation of the whole thing. What do I mean? Let me tell you. You know, although this look like a little bit if you have a more more neuron, it's like you have a lot of you need to write a lot of code, right? For first neuron, for second neuron. No, you don't need to write a lot of code. You can use a matrix. So what do I mean? Let's say for the first neurons, I have a W W11, W12, W1. I want to make it a little bit higher because I have more space for other neuron. W11, W12, W13. How I can calculate this very efficiently? I can use matrix like this. X1, X2, X3. I think it's easy, right? You know what? You just do dot product between this and this, then you get the result. Then amazing thing happen here is like you can also make this another root for this matrix. Right? If you have more neurons, you can keep increase this matrix, right? This will be one matrix. So if you have 100 neurons, that's okay. You just have a 100, you just increase the number of rows to 100. So 101, W102, W103. You have a new matrix, then you do the multiplication. Then what you got is you got A1 and A2, right? You got A1 and A2. That's it. That's how you can implement the neural network. So far so good. Any question for the neural network? Any general question of specific math question and question for implementation? No? Great. Where do I get the weights? I randomly initialize the weight because remember what I say is we need to use gradient descent. How we apply the gradient descent? The gradient descent just let me increase something. The gradient descent just do this. We have beta 0, we have beta 1. It's randomly initialized. I don't care about what value you have. What I care about is I can update it. If I have something, I can calculate the gradient of this. Then I can update it. The thing is I can update it later to make it better. So activation function is same as neuron. Activation function is same as neuron. Actually, neuron is very concrete idea. If let me to choose, I want to say don't use the word neuron. Just forget it. The thing is just you just have linear function, then you apply the nonlinear function on the results of this linear function. Actually, linear combination of the features. So then they call this neuron. They call, okay, here you do this process. What's neuron? Neuron is a processing system. So what's the processing system? The processing system is linear, do the activation function on the output of a linear function. So you can think about activation function of the output of linear function. That's the neuron. Yep, all good. Yep, that's it. Any other question? So actually, this is just a simple nested function, right? If you have function x is a linear function, you have function g is a sigmoid function, so you have new function g f x. So then actually this is just a simple nested function. It's not big deal. So normally, if you want to have a high-level understanding of neuron, what's the idea? The idea is just do some processing of your data. That processing is the neuron. You can say, okay, I don't want this neuron to become same as this neuron. I just make its difference. I just make it a polynomial function. I do something like x1 alpha plus x2 beta plus x3 gamma. I don't know how I can, I just say gamma. So, okay, put this as another neuron. Here is one neuron. But in neural network, we don't do this. Why? Because it's hard to optimize. The way to simplify the optimization is to make it simple, to make it linear, and add some nonlinear outside. Then it will be simple. It's very easy to optimize. That's it. But in the early work of a neural network, maybe last century, I'm not sure because I am not even born at that time. But I do know there are some early papers just don't use this neuron. They just do some other, using other functions for neuron. Okay, all good. Yep. So now I will share my screen to show some code how I can do some implementation. But the key things I want you to know is you have to be familiar with this matrix. You have to familiar with that. Okay, what do I mean? I have a matrix to represent a layer of neural network. It just means this matrix represents different neurons. You know, the first row is one neuron. The second row is another neuron. The third row is third neuron. So that's it. You just need to be comfortable with what's the meaning of the matrix. So this will help you understand the code.